The sun is a burning star, so powerful that even from 93 million miles away, its light warms our oceans, shapes our weather, grows our forests, and gives Earth almost all the energy life depends on. So why is space so cold? It feels like a simple question. If the sun is that hot and space is filled with sunlight, then the space around Earth should feel warm. The moon should hold heat everywhere. Astronauts should be surrounded by warmth. The darkness between planets should not feel like a frozen void. But space does not work like air. On Earth, warmth moves through the atmosphere, through wind, water, ground, and touch. Heat surrounds you because there is matter everywhere to carry it. In space, there is almost nothing. No air to hold warmth, no blanket of atmosphere, no warm wind, no surface around you sharing heat. Only radiation traveling silently through the dark. And that is what makes the universe so strange. The sun can be incredibly hot, while the space around it remains almost empty and cold. Light can cross millions of miles, hit one object and burn it, while a shadow just beside it can become freezing. In space, temperature is not only about sunlight, it is about what absorbs it, what loses it, and whether there is anything there to hold the heat at all. Before we begin, write in the comments where you are watching from and what time it is in your country right now. And if you enjoy calm journeys into the mysteries of space, subscribe to Theories Before Sleep. Tonight, we explore why space is so cold when the sun is so hot, and why the answer is far stranger than it first seems. The first thing we need to understand is that space is not cold in the same way a winter night on Earth is cold. On Earth, cold feels like something that touches you. Cold air touches your skin. Cold wind steals warmth from your body. Cold water surrounds you and pulls heat away much faster. Even the ground beneath your feet can feel cold because your body is constantly sharing energy with whatever it touches. But space is different. Space does not touch you in the same way. There is no air pressing against your skin, no wind, no water, no ground, no invisible ocean of molecules carrying heat away from one place to another. Space is not a cold material wrapped around you. It is almost the absence of material altogether. And that changes everything. When we ask, why is space so cold when the sun is so hot? We are really asking a deeper question. We are asking how heat works when there is almost nothing around to carry it. The sun is unbelievably hot. Its surface is thousands of degrees. Its core is far hotter, a place where pressure and temperature are so extreme that hydrogen atoms are forced together, releasing energy through nuclear fusion. That energy slowly makes its way outward, then escapes as sunlight, spreading through the solar system in every direction. That sunlight reaches Earth. It warms the oceans. It drives the winds. It powers weather, photosynthesis, climate, and almost every living system on our planet. Without the sun, Earth would become a frozen world. So it feels natural to imagine that space near the sun should also be warm. After all, sunlight is everywhere. It shines across the distance between planets. It lights up the moon. It reflects from spacecraft. It reaches Mars, Jupiter, Saturn, and far beyond. If the sun is pouring out that much energy, why does the space between planets remain so cold and dark? The answer is that sunlight is not the same thing as warm air. Sunlight is energy traveling through space, but heat, as we feel it, depends on matter. On Earth, sunlight hits the ground, the ocean, trees, buildings, and your skin. Those surfaces absorb the energy. They warm up. Then they share that warmth with the air around them. The air moves, mixes, rises, falls, and spreads heat across the planet. The atmosphere traps some energy, releases some, and creates a living blanket around the world. Earth feels warm not only because sunlight arrives, but because Earth has material to catch that sunlight. Space does not. Most of space is almost empty. There are particles out there, but so few that they do not behave like air. They are spread across enormous distances. Compared with the atmosphere around you right now, interplanetary space is unimaginably thin. If you could take a handful of air from Earth, it would contain more molecules than a similar volume of space could offer in any ordinary sense. That emptiness is the key. Heat can move in three main ways. Through conduction, when warmth passes through direct contact. Through convection, when moving fluids or gases carry heat around. And through radiation, when energy travels as electromagnetic waves like sunlight. On Earth, all three happen around us constantly. If you touch a hot cup, heat moves into your hand by conduction. If warm air rises from a heater and spreads through a room, that is convection. If you feel warmth from sunlight on your face, that is radiation. But in space, conduction and convection almost disappear because both need matter. There is no air to carry heat away from your body, no atmosphere to move warmth around, no ocean to spread energy, no ground to store heat. So space becomes a place where radiation matters most. Energy can travel through empty space as light, infrared radiation, ultraviolet radiation, and other forms of electromagnetic energy. That is how sunlight reaches Earth. It does not need air. It does not need a wire. It does not need a physical bridge. Radiation can cross the vacuum. But radiation only becomes heat when something absorbs it. This is the part that makes space feel strange. Sunlight can travel through space for millions of miles without warming the empty vacuum, in the way sunlight warms a road or a wall. The light is there, moving through the darkness. But unless it hits something, a planet, a moon, a spacecraft, a grain of dust, an astronaut's suit, there is almost nothing to absorb it and become warm. Space is filled with sunlight near the sun, but space itself has almost nothing to heat. It is like shining a flashlight through a completely empty room. The beam passes through, but if there is no dust, no wall, no floor, no object in its path, there is almost nothing to glow or warm up. The light is present, but the room does not become a warm, solid thing. Now imagine that emptiness on the scale of the solar system. The sun floods space with energy, but most of that energy travels through the void until it strikes matter. Earth catches a tiny fraction of it. Mars catches a smaller fraction. Jupiter catches even less per square meter because it is farther away. A spacecraft catches only the sunlight that falls on its surface. The rest continues outward, thinning as it spreads. This is why distance also matters. Sunlight weakens with distance because the sun's energy spreads out in all directions. Close to the sun, the same amount of energy is concentrated into a smaller area. Farther away, that energy is spread across a much larger sphere. By the time sunlight reaches the outer planets, It is much weaker than it is at Earth. But even near Earth, where sunlight is still strong, empty space does not become warm like air. There is nothing there to hold the warmth. That is one of the most important differences between Earth and space. Earth has an atmosphere. The atmosphere does not only give us air to breathe, it also helps regulate heat. It absorbs, scatters, and traps energy. It allows heat to move through wind and weather. It softens the extremes between day and night. It creates a world where temperature is not only determined by direct sunlight, but by a complex system of air, water, clouds, oceans, land, and greenhouse gases. The moon is different. The moon has no thick atmosphere. So even though it is about the same distance from the sun as Earth, its temperature changes are extreme. In sunlight, the lunar surface can become very hot. In shadow, it can become brutally cold. There is no air to spread heat from the bright side into the dark side, no wind to soften the difference, no ocean to store warmth, no thick blanket around the moon to hold heat through the night. This shows us the real nature of space. It is not simply cold everywhere. It is extreme. A surface in sunlight can heat up dramatically. A surface in shadow can radiate its heat away and become freezing. The difference between light and shadow in space can be enormous because there is no atmosphere to blend them together. This is why spacecraft are so difficult to design. Engineers do not only worry about freezing, they also worry about overheating. A spacecraft near Earth can have one side facing the sun and another side in darkness. The sunlit side may absorb energy and become hot, while the shaded side loses heat to space. Without careful thermal control, the spacecraft could be damaged by both extremes. It needs insulation, reflective surfaces, radiators, heaters, and careful design to keep its instruments within safe temperatures. That may sound surprising. Space is cold, and yet spacecraft can overheat. But once we understand radiation, it makes sense. A spacecraft in sunlight absorbs energy. A spacecraft also emits energy as infrared radiation. Its final temperature depends on the balance between what it absorbs and what it loses. If it absorbs more energy than it radiates away, it warms up. If it radiates away more energy than it absorbs, it cools down. The vacuum of space does not provide a stable temperature the way air does. It creates a battlefield between sunlight, shadow, absorption, and radiation. This is why the phrase "space is cold" can be misleading. The empty vacuum does not have a simple temperature like a room. Temperature usually describes the average motion of particles. In air, there are many particles moving around, colliding with your skin, transferring energy. In space, there are so few particles that ordinary temperature becomes harder to imagine in the same everyday way. A lonely atom in space can have a high energy. A nearby surface can be freezing. A sunlit spacecraft can be hot. A shaded instrument can be cold. A planet with an atmosphere can be warm. A nearby vacuum can still feel like nothing at all. Space is not one temperature. It is an environment where heat has very few ways to move, except by radiation. This is also why shadows in space are so powerful. On Earth, if you step into shade, you usually do not instantly freeze. The air around you still has warmth. The ground still radiates heat. Nearby objects share energy. The atmosphere scatters sunlight. Even in shade, the world around you remains part of a thermal system. On the moon, shade is much more severe. A shadowed crater near the lunar poles may remain dark for incredibly long periods. Without direct sunlight and without an atmosphere to carry warmth into it, such a region can become extremely cold. Some of these permanently shadowed areas may trap ice because they act like cold storage chambers, protected from the sun for vast spans of time. That is the power of darkness in space, not because darkness itself is a substance, but because without sunlight and without surrounding matter to bring heat in, an object can keep radiating energy away until it becomes very cold. This is the same reason the deep universe has a background chill. Far from stars, planets, and warm surfaces, objects lose heat into space. Eventually, if they receive very little energy from nearby stars, they cool toward the faint temperature of the cosmic microwave background, the ancient afterglow of the early universe. That background is only a few degrees above absolute zero. It is not completely zero, because the universe still carries this ancient radiation everywhere, but it is incredibly cold. So space can be filled with radiation and still be cold. The sun fills the solar system with light. The cosmic microwave background fills the universe with ancient radiation. Distant stars shine in every direction. But between the stars, matter is so thin and energy is so spread out that objects can cool dramatically if they are not close enough to a strong heat source. This is where the paradox begins to fade. The sun is hot. Space is cold. Both are true because heat needs a receiver. The sun is a source of energy. Space is mostly emptiness. A planet, moon, asteroid, or spacecraft becomes warm only when it absorbs energy faster than it loses it. Earth stays habitable because it has the right distance from the sun, an atmosphere, oceans, clouds, rotation, and many systems that move and store heat. The moon does not. A spacecraft must create its own thermal balance. An astronaut's suit must protect against both heating and cooling. The vacuum itself does not behave like a cold wind, but it allows heat to escape by radiation into a very dark background. This is one reason space feels so alien. On Earth, temperature surrounds us. In space, temperature depends on exposure. Face the sun, and energy arrives. Turn into shadow, and the heat begins to leave. Touch nothing, and there is no conduction. Float in vacuum, and there is no convection. You are left with radiation, a silent exchange of energy between objects and the darkness. This gives space its strange cruelty. It does not cool you by blowing cold air over you. It cools you by giving your heat nowhere to go, except away from you as light. And at the same time, it can burn exposed surfaces with unfiltered sunlight. There is no comfort in the middle unless you build it. Every spacecraft is a small artificial climate. Every spacesuit is a tiny world. Every space station is a controlled island of warmth, pressure, and balance, floating in an environment that offers none of those things naturally. The International Space Station orbits Earth in sunlight and shadow, again and again. It moves from bright solar exposure into Earth's shadow many times a day. Outside its walls, the thermal environment changes violently. Inside, humans live in controlled air, with systems constantly working to manage temperature, remove heat, circulate atmosphere, and keep the station livable. The station does not survive because space is gentle. It survives because engineering creates a pocket of Earth-like conditions in a place where Earth-like conditions do not exist. This is the hidden truth behind every human presence in space. We do not live in space. We bring a tiny version of Earth with us. Air, pressure, warmth, water, protection. Without those systems, space does not support the familiar meaning of temperature, comfort, or survival. It is not simply cold. It is indifferent. If you are in sunlight, it gives you radiation. If you are in shadow, it gives you darkness. If you lose heat, it does not return it. If you need air to carry warmth, there is none. That is why the sun can be hot and space can remain cold. They are not opposites in the way we first imagine. The sun is a furnace. Space is the empty room around it. The furnace can send light across the room, but the room itself is not filled with warm air. Only the objects struck by that light heat up. Only surfaces, particles, and worlds that absorb energy become warm. Between them, the emptiness remains almost nothing. And this brings us back to Earth. Our world is not warm simply because the sun exists. It is warm because it catches sunlight and holds just enough of it. The atmosphere softens the extremes. The oceans store heat. The ground absorbs and releases energy. Clouds reflect sunlight. Greenhouse gases trap some infrared radiation. Winds and currents move warmth around the globe. Earth is not just a rock under the sun. It is a living thermal system. A balanced world in a universe that is mostly unbalanced. That balance is fragile. Too little atmosphere, and Earth might lose heat too quickly. Too much trapping of heat, and the surface could become dangerous. Too far from the sun, and water freezes. Too close, and oceans can vanish. The fact that Earth has stayed within a range where liquid water and life could persist for billions of years is not something to take lightly. Against the cold emptiness of space, Earth is a miracle of moderation. A blue planet wrapped in air. A world that catches starlight and turns it into weather, water, forests, and life. The sun gives the energy. Earth makes it livable. And space around us remains mostly cold because it has no ocean, no air, no soil, no blanket, and almost no matter to hold that energy. So when we look up at the sun, we are seeing a star powerful enough to warm a planet from 93 million miles away. But when we look into the darkness around that star, we are seeing the other side of the truth. Energy can travel through emptiness, but emptiness does not become home. Space is cold not because the sun is weak. Space is cold because the universe is vast, thin, and mostly empty. Warmth belongs to the places that can catch it, and Earth, for now, is one of those places. The strangest thing about space is that it can be filled with sunlight and still feel empty of warmth. This sounds impossible at first. On Earth, when sunlight fills a room, the room becomes brighter and often warmer. When the sun rises over a desert, the sand heats up. When sunlight falls on your skin, you feel it almost immediately. Our bodies are used to a world where light, air, ground, and warmth work together. The sun shines. Surfaces absorb the light. The air moves around those surfaces, and heat spreads through the environment. But space removes almost all of that. It gives us the light, but not the room. It gives us the radiation, but not the air. It gives us the energy, but not the comfortable world that holds it. This is why the same sunlight that warms Earth can pass through empty space without making space itself feel warm in the way we expect. The energy is there, traveling silently in straight lines. But unless that energy hits matter, It remains only radiation moving through darkness. A beam of sunlight crossing space is not like warm air filling a house. It is more like a stream of invisible messengers. Each one carries energy. Each one can warm something, but only if it is received. This is the key to understanding the solar system. Every planet, moon, asteroid, spacecraft, and grain of dust is constantly negotiating with sunlight. It absorbs some energy, it reflects some away. It radiates energy back into space. Its temperature depends on the balance between incoming and outgoing energy. Space itself does not decide the temperature, the object does. A black rock near the sun may become extremely hot because it absorbs a lot of sunlight. A shiny reflective surface may stay cooler because it sends much of the light away. A planet with an atmosphere may trap heat. A moon with no atmosphere may swing between burning sunlight and freezing shadow. A spacecraft may need to rotate, reflect light, or release heat through radiators just to survive. In space, temperature is not one simple number. It is a relationship between light and darkness, between absorption and reflection, between distance and exposure, between matter and emptiness. This is why two objects in the same place can have very different temperatures. Imagine a white spacecraft panel and a dark asteroid sitting at the same distance from the sun. The dark asteroid may absorb more sunlight and heat up more quickly. The white panel may reflect more light and remain cooler. Add a shiny metallic coating, and the behavior changes again. Add insulation, and the object may keep heat longer. Add radiators, and it can release heat more efficiently. Space is not telling them one temperature. Each surface is answering sunlight in its own way. This is also why the moon is such a powerful example. The moon sits almost the same distance from the sun as Earth. It receives nearly the same intensity of sunlight. But the moon has no thick atmosphere, no oceans, no weather, and no global system to move heat around. When sunlight hits the lunar surface, the ground can become extremely hot. But when a region falls into darkness, it begins losing heat directly to space. There is no warm air to blow across the surface, no clouds to trap energy, no ocean to store daytime heat and release it slowly at night. The moon is exposed, and exposure creates extremes. The same world can be hot enough to bake in sunlight and cold enough to freeze in shadow. This is not because the moon is farther from the sun. It is because it cannot hold and distribute heat the way Earth can. Earth is different because Earth has a blanket, not a blanket made of cloth, but an atmosphere. That atmosphere changes everything. It catches some of the outgoing infrared radiation from the surface. It moves heat through wind. It carries water vapor. It forms clouds. It allows storms, pressure systems, circulation, and climate. The oceans absorb enormous amounts of energy during the day and release it slowly. Land heats and cools faster, but the atmosphere connects everything into a larger system. Earth does not simply sit under sunlight. Earth processes sunlight. That is why our planet has a stable range of temperatures compared with airless worlds. The sun gives energy, but Earth's atmosphere and oceans make that energy livable. Without them, our world would be far more extreme. The days would be harsher. The nights would be colder. The difference between light and shadow would become much more dangerous. This is one of the hidden miracles of living here. We do not feel the raw solar system. We feel Earth's protection. When you stand outside on a sunny day, you are not experiencing space directly. You are experiencing sunlight filtered through atmosphere, softened by air, scattered by molecules, balanced by the ground and water around you. Even the blue sky is a sign that the atmosphere is interacting with sunlight. Even shade on Earth still has warmth because the air around you remains connected to the larger environment. In space, shade is not like shade on Earth. Shade in space can be a doorway into deep cold. Not instantly, not magically, but physically. An object in shadow no longer receives direct sunlight. It continues radiating its own heat away into the darkness. If nothing nearby warms it, and if it has no internal heat source, it can cool dramatically. The object becomes like a small island, losing energy to an enormous silent universe. This is why some places near the moon's poles are so cold. There are craters where sunlight may never reach the bottom. The sun stays low near the horizon, and the crater walls keep the floor in permanent shadow. These regions can remain cold for extremely long times. They may preserve ice because the heat needed to remove it rarely arrives. They are like natural cold traps, not because the moon is always freezing, but because shadow in vacuum is powerful. A place can be close to the sun and still be extremely cold if sunlight cannot reach it. That idea feels strange because on Earth, heat spreads sideways, warm air moves, water circulates, ground conducts heat. But on the moon, and in much of space, heat does not spread easily through empty surroundings. A sunlit rock and a shadowed crater can exist near each other with a massive temperature difference. The vacuum allows sharp contrasts. It does not smooth them. This also affects spacecraft. A spacecraft orbiting Earth can move from sunlight into Earth's shadow again and again. Each time, its thermal environment changes. One moment, sunlight strikes its surfaces directly. The next, it is in darkness, radiating heat away. Instruments, batteries, cameras, fuel lines, and electronics all need temperatures within safe ranges. Too hot, and they fail. Too cold, and they fail. Spacecraft do not survive because space is naturally comfortable. They survive because engineers carefully control heat. They use insulation that slows heat loss. They use reflective materials that reduce unwanted sunlight absorption. They use dark radiators that release excess heat. They use heaters to protect sensitive parts during cold periods. They sometimes rotate spacecraft to spread sunlight more evenly. Everything is planned because space gives no natural balance. This is one of the reasons spacecraft often look strange. Gold foil, white surfaces, black radiators, mirrored coatings, these are not decorations. They are thermal tools. They decide how the spacecraft interacts with sunlight and with the cold darkness around it. A spacecraft is not only a machine for movement or communication. It is a machine for surviving heat exchange. In space, heat management is survival. The International Space Station is a perfect example. Inside, astronauts live in a controlled environment with air, pressure, and livable temperatures. Outside, the station faces extreme cycles of sunlight and shadow as it orbits Earth. It needs systems to remove heat generated by electronics, sunlight, and human activity. It also needs protection against cold in shadow. The station is not simply kept warm, it is kept balanced. That word matters. Balanced. Space is not only cold, it is unbalanced. One side can overheat while another side freezes. One instrument can be exposed to sunlight while another is in darkness. The inside of a spacecraft can build up heat because electronics are running, even while the outside radiates energy away. Heat cannot simply float into surrounding air because there is no surrounding air. So engineers must guide heat deliberately. On Earth, if a computer gets warm, air can carry some of that heat away. Fans help. The room absorbs some warmth. On a spacecraft, heat has fewer escape routes. It can move through solid materials inside the craft, and it can be radiated into space. But it cannot be carried away by ordinary air outside. This makes cooling in space more difficult than people imagine. Again, the vacuum changes everything. It prevents heat from moving by convection. It also prevents cold from touching you like wind. This is important because movies often make space look like instant freezing. But reality is more subtle. If something is exposed to vacuum, there is no cold air to rush over it. Heat is lost mainly by radiation, and sometimes by evaporation or other physical processes depending on the object. Cooling can be fast in some conditions and slower in others. It depends on surface area, material, temperature, sunlight, shadow, and internal heat. Space is deadly, but not because it behaves like an icy wind. It is deadly because it removes pressure, air, protection, and stable heat exchange. Temperature is only one part of the danger. For human life, the problem is that our bodies are built for Earth. We are built for air pressure, oxygen, liquid water, and a narrow temperature range. We are not built for vacuum. A spacesuit is not just clothing. It is a miniature spacecraft wrapped around the body. It provides pressure, oxygen, cooling, insulation, and protection from radiation and micrometeoroids. A spacesuit must protect an astronaut from heat and cold at the same time. In sunlight, the suit can absorb intense solar energy. In shadow, it can lose heat. The astronaut inside also produces body heat, and that heat must be removed or controlled. Without cooling, the astronaut could overheat inside the suit even while surrounded by the cold vacuum of space. That may be the most surprising part. In space, overheating can be as serious as freezing. Because there is no air to carry body heat away, the suit has to manage it. The astronaut is not simply trying to stay warm. They are trying to stay within a narrow zone where the body can function. Too much heat is dangerous. Too much heat loss is dangerous. The suit becomes a climate system, not just a shield. This teaches us something deeper about Earth. Our planet is the greatest spacesuit we have. The atmosphere surrounds us with pressure and warmth. It carries oxygen. It protects us from much of the sun's dangerous radiation. It allows heat to move gently enough for life. It holds water in liquid form. It makes the difference between day and night survivable. It turns raw sunlight into climate. Without that planetary spacesuit, Earth would not feel like Earth. It would feel more like a rock in space. This is why the question, why is space so cold when the sun is so hot, eventually becomes a question about habitability. A hot star is not enough. A planet needs the right relationship with that star. It needs distance. It needs atmosphere. It may need oceans. It needs the ability to hold heat without trapping too much. It needs protection from extremes. Mercury shows us one side of the problem. It is the closest planet to the Sun, and its day side can become extremely hot. But Mercury has almost no atmosphere to distribute heat. Its night side can become extremely cold. The closest planet to the Sun still experiences deep cold when turned away from sunlight. That alone proves the point. Proximity to the Sun does not guarantee comfortable warmth. Without an atmosphere, heat remains local and temporary. Venus shows the opposite extreme. Venus is farther from the Sun than Mercury, but it is far hotter at the surface because of its thick atmosphere and powerful greenhouse effect. Its atmosphere traps heat so efficiently that the planet becomes a furnace. This shows that temperature is not only about distance from the Sun. It is also about what a planet does with the energy it receives. Earth sits between these extremes, not too exposed like Mercury, not trapped like Venus, wrapped in an atmosphere strong enough to warm and protect, but not so extreme that oceans boil away. This balance is why liquid water can exist across much of the surface. It is why life has had time to grow complex. It is why the Sun's heat becomes not only energy, but weather, seasons, rain, rivers, forests, and breath. Mars shows another lesson. Mars receives less sunlight than Earth because it is farther from the Sun. It also has a thin atmosphere that cannot hold heat well. Its surface can warm in sunlight, but temperatures drop sharply, especially at night. Mars is not cold simply because it is farther from the Sun. It is cold because it receives less energy and has too little atmosphere to keep much of it. Each planet answers sunlight differently. Mercury receives a lot, but cannot hold it. Venus receives less than Mercury, but traps it intensely. Earth receives enough and balances it. Mars receives less and loses it quickly. The outer planets receive far less sunlight, and their worlds depend more on internal heat, atmospheres, and distant solar energy. Moons far from the Sun can be icy, yet some may hide internal oceans warmed by tidal forces. Again, sunlight is not the only actor. Heat can come from gravity, radioactive decay, planetary formation, and internal processes. Space is cold, but worlds can find warmth in different ways. This is one of the reasons ocean moons are so fascinating. Europa, Enceladus, and other icy bodies are far from the warmth of the inner solar system, yet may have liquid water beneath their frozen surfaces. They are not warmed mainly by sunlight. They are warmed by internal energy, especially tidal flexing, caused by gravitational interactions with giant planets. Their surfaces may be freezing, but their interiors may be active. The universe is full of these contrasts. A frozen surface can hide an ocean. A hot sun can shine through cold space. A planet in shadow can freeze beside a sunlit surface. A spacecraft can overheat in a vacuum. Temperature in space is never as simple as our instincts want it to be. Because our instincts were shaped on Earth, where heat is carried by air, water, soil, and living systems. Space removes that familiar world and leaves only the basic physics: radiation, matter, distance, absorption, emission, and time. When sunlight leaves the Sun, it begins spreading across an enormous sphere. Every second, the sphere grows larger. The same energy becomes thinner with distance. At Earth, the sunlight is still powerful enough to sustain life. At Mars, weaker. At Jupiter, weaker still. At Pluto, sunlight is faint compared with what we know, though still far brighter than moonlight on Earth. The farther you go, the less solar energy each square meter receives. This is why the outer solar system is so cold. Not because the sun has vanished, but because its energy has spread thin across billions of kilometers. The sun remains hot, but distance dilutes its warmth. This dilution follows a simple idea: spread the same light over a larger and larger area, and each piece receives less. It is like moving away from a campfire. The fire itself has not cooled, but you receive less heat because you are farther away. In space, the effect is much more precise and enormous. Double the distance, and sunlight becomes much weaker per unit area. By the time you reach the outer planets, sunlight is only a pale version of what Earth receives. Yet even there, sunlight still matters. It lights clouds, faintly warms surfaces, and helps shape atmospheres. But it is not enough to make those distant worlds warm like Earth. They are too far, and much of their warmth must come from other sources, if any. This gives the solar system a thermal geography. Near the sun, sunlight dominates. Farther out, it weakens. Airless bodies swing between extremes. Thick atmospheres can trap heat. Icy moons can hide internal oceans. Gas giants can radiate leftover heat from their formation. Space between them remains almost empty. The coldness of space is not a single fact. It is the result of a universe where matter is rare and distance is enormous. In the end, the sun can be hot because it is dense, massive, and powered by fusion. Space can be cold because it is thin, vast, and almost empty. There is no contradiction. A furnace can burn in the middle of a huge empty hall, and the hall can still feel cold where the light does not land. The sun is the furnace. The solar system is the hall. The planets are the objects that catch the heat. Earth is one of the rare objects that catches it beautifully. And that is what makes our world so special. We do not simply live near a star. We live on a planet that knows how to use one. Earth catches sunlight, softens it, moves it, stores it, and turns it into the conditions of life. The atmosphere and oceans make the sun's energy gentle enough for forests, clouds, animals, and human beings. Around us, the vacuum waits, cold not like winter air, but like emptiness itself. The sun is hot, space is cold, and Earth is the fragile balance between them. The coldness of space becomes even stranger when we realize that darkness itself is not what makes things cold. Darkness is only the absence of light. It is not a substance. It does not blow. It does not wrap around a planet like icy air. It does not push cold into an object. In space, a shadow is powerful because it cuts an object off from the main source of energy nearby. Once sunlight is gone, the object has only one direction left for its heat to go: away, silently, as infrared radiation. This is one of the most important differences between Earth and the vacuum beyond it. On Earth, when night falls, the surface cools, but not into instant deep freeze. The atmosphere keeps moving. Clouds can trap warmth. Oceans release stored heat. Winds carry warm air from one region to another. The ground itself gives back energy it collected during the day. Even at night, Earth remains connected to a huge thermal system. But in space, when something enters shadow, it can become isolated. There is no warm air around it, no blanket of atmosphere, no nearby ground spreading heat through contact, only the object's own stored energy. slowly escaping into the universe. This is why a spacecraft, a moon rock, or an astronaut suit can experience extreme changes depending on whether it faces the sun or turns away from it. The sun may be blazing nearby in astronomical terms, but if direct sunlight is blocked, the local environment can shift dramatically. A surface that was heating under solar radiation can begin to cool as soon as the energy source disappears, not because cold attacks it, but because warmth leaves. That single idea helps explain so much of space. Cold is often not something entering, it is heat escaping. On Earth, we feel cold as a presence because air and water actively pull heat from us. But in space, cold is more like a permission. The vacuum allows heat to leave and gives very little back. If an object has no sunlight, no internal energy, and no nearby warm surface, it can radiate its heat into a background that is incredibly cold. And this background is one of the deepest answers to the question. Far from stars, far from planets, far from warm dust and glowing gas, the universe has a faint temperature left over from its earliest history. This is the cosmic microwave background, the ancient afterglow of the Big Bang. It fills space in every direction, but it is extremely weak now, only a few degrees above absolute zero. Absolute zero is the lowest possible temperature, the point where thermal motion is minimized as much as nature allows. The universe is not at absolute zero, but deep space is very close compared with anything familiar on Earth. The cosmic background is like a fading warmth from the young universe, stretched and cooled by billions of years of expansion. So even the deepest darkness is not truly nothing. It carries a faint ancient glow. But that glow is so weak that compared with the sun, it is almost unimaginably cold. This is why an object drifting far from any star would slowly cool toward that background. It would not instantly become the same temperature, and the process would depend on its material, size, shape, internal heat, and how much radiation it receives. But without a strong nearby energy source, the direction is clear. Heat leaves, the object cools. The universe receives the radiation and barely answers. This makes deep space feel like an enormous silent sink for heat. Anything warm can radiate energy into it, but the universe gives back only a faint whisper, unless a star, planet, or other source is nearby. The sun changes that balance in the solar system. Near the sun, sunlight is strong. Objects absorb it and warm up. But the sun's energy spreads outward in all directions, becoming thinner with distance. By the time sunlight reaches Earth, it is still powerful. By Mars, weaker. By Jupiter, much weaker. By Saturn, faint. By Neptune, sunlight is only a tiny fraction of what Earth receives. The farther you go, the less warmth there is to catch. This is why the outer solar system is so cold. Not because the sun has stopped being hot, but because the sun's light has spread across such a huge sphere that each square meter receives very little energy. The outer planets still reflect sunlight. Their moons still cast shadows. Spacecraft can still use sunlight to take images, but the warmth is diluted. A star can be incredibly powerful and still become faint with distance. A campfire gives a smaller version of this truth. Close to a fire, your face warms. Step back, and the heat fades. The fire did not become cooler. You are simply receiving less energy. Now imagine stepping back, not across a room, but across billions of kilometers. That is what the outer planets experience. The sun is still the sun, but the energy arriving at each surface is much weaker. This is why Pluto is so cold. The sun from Pluto is still bright compared with other stars, but it is no longer the overwhelming source of warmth it is for Earth. It becomes a distant lamp in a black sky, powerful enough to cast light, but not enough to create Earth-like heat. The surface remains frozen because the energy arriving there is too weak, and because there is no thick, warm atmosphere like Earth's to soften the cold. Still, even Pluto is not the deepest cold the universe can offer. Beyond the planets, beyond the Kuiper belt, beyond the distant icy bodies and comets, the sun fades further. The interstellar medium begins. Stars become separate lights rather than one dominant furnace. In those spaces, any object without internal heat is at the mercy of faint radiation from distant stars and the cosmic background. This is the cold between stars. A cold not like winter, not like ice on Earth, not like wind over snow. A cold created by separation, by thinness, by the absence of matter, by the lack of nearby energy. And yet, even there, space is not uniform. Some regions are filled with hot gas from supernova explosions. Some clouds are cold and dense. Some areas are bathed in radiation from young massive stars. Some are near glowing nebulae. Some are almost empty. The universe is not one single temperature. It is a patchwork of environments. A gas cloud can be cold enough to collapse into future stars. A supernova remnant can contain gas heated to extreme temperatures. A dust grain near a star can become warm. A planet in shadow can freeze. A telescope shielded from the sun can cool deeply. Space is not simply cold everywhere. It is thermally uneven. What matters is the balance of energy. This balance is why scientific instruments in space often need careful cooling. Many telescopes are designed to detect faint infrared light, which is heat radiation. But if the telescope itself is warm, its own heat can interfere with the faint signals it is trying to observe. It would be like trying to hear a whisper while standing beside a loud engine. So some space telescopes are designed to stay extremely cold. They use sunshields, radiators, special orbits, and careful positioning to block sunlight and allow heat to escape into space. The goal is to make the telescope quiet in infrared, so it can detect faint heat from distant stars, galaxies, planets, and dust clouds. In this case, the coldness of space becomes useful. It allows instruments to cool in a way that would be impossible on Earth without complex machinery. But even then, the telescope must be protected from the sun. If sunlight hits it directly, it warms. If Earth's heat reaches it, it warms. If its own electronics produce heat, that heat must be managed. So once again, space is not just cold. It is a place where temperature depends on direction. Face the sun, and heat arrives. Hide from it, and heat can drain away. Point toward Earth, and infrared energy from our planet matters. Point into deep space, and the universe becomes a cold background. This is why shadows in space can be engineered. A sunshield can create artificial night. One side may face the sun and become warm. The other side may face deep space and remain extremely cold. A thin structure can separate two thermal worlds, sunlight on one side, darkness on the other. On Earth, that would be impossible in the same extreme way, because air would carry heat around the barrier. In space, the vacuum prevents that easy mixing. The vacuum allows one side to be hot and the other side to be cold. This same idea appears on planets and moons without atmospheres. The moon's day side and night side do not share heat efficiently. Mercury, though close to the sun, can still have freezing regions because it has almost no atmosphere. Asteroids can heat quickly in sunlight and cool quickly in shadow. Small bodies with little insulation can experience intense surface temperature swings. The solar system is full of surfaces answering sunlight differently. Some absorb, some reflect, some store heat, some lose it rapidly, some hide ice in permanent darkness, some trap warmth under thick atmospheres. Every world is a different thermal story. Earth's story is unusual because it has moderation. The atmosphere and oceans prevent the worst extremes. The planet rotates, but not so slowly that one side bakes endlessly while the other freezes for too long. The atmosphere carries heat from day to night, from equator to poles, from oceans to continents. Clouds reflect sunlight and trap infrared radiation. Ice reflects light. Forests, deserts, seas and storms all participate in the flow of energy. Earth turns sunlight into climate. Space does not. That is the difference. Space receives sunlight, but it does not process it into comfort. It does not have winds. It does not have weather. It does not have a surface everywhere. It does not have a global ocean of air carrying warmth from one place to another. It is mostly a stage on which objects interact with radiation individually. This makes Earth feel almost miraculous, not because it is the only warm place. Venus is warm, far too warm. Gas giants have internal heat. Moons may hide oceans. Stars burn everywhere. But Earth has the kind of warmth life can live with on the surface. Not perfect everywhere, not always gentle, but stable enough for billions of years of evolution. Stable enough for water, clouds, seasons, forests, and bodies that are mostly liquid water. When you compare that to the surrounding vacuum, Earth becomes less like a rock and more like a protected island of temperature, a small region where heat is caught and shaped, a place where the sun's violence is softened into daylight. The sun itself is not gentle. At its core, matter is compressed under unimaginable pressure. Fusion releases energy that slowly travels outward through the star. By the time it reaches the surface, the sun shines into space as light and heat. That energy can damage unprotected materials, strip atmospheres over time, drive space weather, and flood the inner solar system with radiation. Earth survives not by being exposed to the sun raw, but by filtering it. Our atmosphere blocks much of the dangerous ultraviolet radiation. The magnetic field helps guide charged particles around the planet. The ozone layer absorbs harmful wavelengths. Clouds and ice reflect some sunlight back into space. Greenhouse gases trap some outgoing heat. The system is delicate, complex, and constantly moving. From space, Earth looks calm. Blue, white, beautiful. But that beauty is the visible face of a thermal balance. Too much sunlight absorbed, and the planet warms. Too much reflected, and it cools. Too much heat trapped, and climate changes. Too little atmosphere, and the surface becomes harsher. A habitable planet must live between extremes. The sun gives energy, but balance gives life. This is why the question of cold space and hot sun leads to the question of life itself. Life as we know it needs liquid water, chemistry, and stable conditions over time. Those conditions depend on heat, not too much, not too little, not only for a day, but over geological time. Space offers no such stability by default. A planet must create it, or receive it, or hide it. Some worlds may do this beneath ice. Europa, orbiting Jupiter, is far from the Sun and covered in a frozen shell. Yet tidal forces may keep an ocean liquid beneath the surface. Enceladus, a small moon of Saturn, releases plumes from its south polar region, suggesting hidden liquid water inside. These worlds remind us that warmth can come from gravity as well as sunlight. The Sun is not the only heat source. Planets and moons can carry internal heat from formation, radioactive decay, and tidal flexing. Giant planets can radiate more energy than they receive from the Sun. Some worlds may be dark on the outside and active within. A moon can look frozen and still hide movement below. This makes the solar system more mysterious. Cold surfaces do not always mean dead interiors. A frozen world can have a warm heart, but the opposite can also be true. A sunlit surface does not always mean a livable world. Mercury receives intense sunlight, yet it has no comfortable surface environment. Venus receives sunlight and traps heat so severely that its surface is hostile. Mars receives less sunlight and has too little atmosphere to hold warmth. The Moon receives Earth-like sunlight but lacks the systems to make it stable. Earth's warmth is not a simple result of distance. It is the result of relationship. Sunlight, atmosphere, water, rotation, chemistry, and time all working together. This relationship is fragile, and it is rare in the only universe we can actually observe. We have found many planets beyond the solar system, but knowing whether they are truly habitable is difficult. A planet may be the right distance from its star and still have the wrong atmosphere. It may have water, but too much radiation. It may be tidally locked, with one side facing its star forever. It may be too young, too old, too dry, too volcanic, too frozen, or too unstable. Warmth alone does not make a home. A star alone does not make a world livable. The Sun is hot, but space around it remains cold, because heat is not simply spread like soup through the solar system. It is exchanged, absorbed, reflected, trapped, and lost. The solar system is not a warm room. It is a mostly empty arena where every object must manage energy in its own way. Earth manages it beautifully. That is why we are here. If Earth had no atmosphere, the sun would still shine, but the world would be harsher. If Earth were farther away, the same atmosphere might not be enough. If it were closer, the oceans might not survive. If the atmosphere were much thicker or chemically different, the surface could become unrecognizable. Habitability is not one condition. It is a balance of many, and balance is delicate. This is where the coldness of space becomes emotional. It reminds us that warmth is not guaranteed. The universe is not naturally comfortable. Most places are not built for bodies, oceans, forests, or breath. Most of the solar system is airless, frozen, irradiated, crushing, burning, or empty. Most of interstellar space is unimaginably thin and cold. The warmth we know is not the default state of reality. It is a local arrangement, a temporary success, a rare pocket of balance around a star. When sunlight touches your face on Earth, it has already traveled through space for more than 8 minutes. It left the sun, crossed the vacuum, entered the atmosphere, scattered through the sky, struck the ground, warmed the air, and became part of the living world around you. That warmth feels simple because your body was born inside it. But from the universe's point of view, it is extraordinary. A star releases energy, a planet catches it, an atmosphere softens it, an ocean stores it, life uses it, and minds eventually ask why space around it is so cold. That question reveals how unusual our situation is. We live between fire and emptiness. The sun is the fire. Space is the emptiness. Earth is the balance. Every day, our planet receives sunlight, reflects some away, absorbs some, radiates heat back into space, and keeps enough to remain alive. This exchange never stops. Earth is constantly speaking thermally with the universe, taking in visible light, sending out infrared radiation, holding enough warmth to keep oceans liquid. The coldness of space is part of that balance too. If Earth could not radiate heat away, it would overheat. If it radiated too much, it would freeze. The cold, dark sky is not only a threat, it is also the place where Earth releases excess heat. Our planet survives because it can both receive and let go. That is a beautiful thought. Life depends not only on the sun's warmth, but also on the universe's coldness. Too much heat would destroy habitability. Too little heat would freeze it. Between the hot sun and cold space, Earth finds a narrow path, a living path, a blue path, a path where clouds drift, rain falls, oceans move, forests grow, and humans look up into the dark and wonder why it feels so cold beyond the sky. The answer is not that the sun is too weak. The answer is that space is too empty to become warm in the way Earth does. The sun sends energy. Matter catches it. Atmospheres shape it. Worlds either hold it, lose it, or are transformed by it. And in that quiet exchange, every planet becomes its own answer. Mercury answers with extremes. Venus answers with trapped fire. Mars answers with thin, cold air. The moon answers with sunlight and shadow. Europa answers with ice and hidden warmth. Earth answers with life. And space itself remains the silent background. Not dead, not empty in every sense, but vast, thin, dark, and patient, cold enough to receive the heat of worlds, wide enough to let starlight travel for billions of years, and strange enough that a hot sun can burn at the center of our days, while the universe around it remains almost impossibly cold. The coldness of space becomes most real when humans try to survive inside it. From Earth, space can look calm. The stars are still. The moon is silent. The darkness between planets seems almost peaceful. But for any machine, any spacecraft, or any astronaut leaving our atmosphere, space is not gentle. It is not simply a cold place waiting quietly beyond the sky. It is an environment where heat must be controlled every second. Too much heat can destroy equipment. Too little heat can freeze systems. A sudden shadow can change everything. A surface facing the sun can become dangerously hot, while another surface only meters away can lose heat into darkness. This is the strange thermal world beyond Earth, a world where there is no natural comfort, only balance. On our planet, we almost never think about how much the environment helps us. Air moves heat away from our bodies. Buildings hold warmth. Water absorbs energy. Clouds soften sunlight. The ground beneath us stores heat during the day and releases it at night. Even when we feel cold, we are still surrounded by matter. Air is touching us. The world is sharing energy with us. But in space, you cannot depend on the world. There is almost no world there. A spacecraft has to become its own world. Every human spacecraft is a small bubble of Earth surrounded by a vacuum that offers no air, no pressure, no natural temperature control, and no forgiving atmosphere. Inside the spacecraft, people may be breathing, working, sleeping, eating, and floating in controlled warmth. Outside, the same spacecraft may be crossing from sunlight into shadow, receiving radiation from the sun, reflecting heat from Earth, and releasing energy into the darkness. The walls between those two realities are thin. A few layers of metal, insulation, wiring, sensors, radiators, and careful designs separate life from the raw physics of space. This is why thermal control is one of the hidden miracles of spaceflight. When people imagine a spacecraft, they often think of engines, rockets, windows, computers, and communication antennas. But one of the most important parts of the design is something quieter: how the spacecraft handles heat. It must keep the crew warm enough. It must keep electronics cool enough. It must stop fuel lines from freezing. It must prevent batteries from overheating. It must protect cameras, sensors, and instruments from temperature swings. It must allow heat to leave when there is too much and preserve heat when there is too little. A spacecraft is not only traveling through space, it is constantly negotiating with temperature. And the negotiation never ends. The International Space Station shows this beautifully. It orbits Earth roughly every 90 minutes, moving again and again from sunlight into Earth's shadow. For part of each orbit, the sun shines directly on the station. Then the station passes behind Earth, and the sunlight disappears. Outside, the thermal environment changes rapidly. Inside, astronauts continue living in a controlled atmosphere, often without feeling the full violence of those changes. That comfort is artificial. It is created. The station uses insulation, heaters, radiators, cooling loops, sensors, and constant monitoring. Electronics inside the station generate heat. Human bodies generate heat. Sunlight adds heat. Equipment adds heat. If all that heat stayed inside, the station could become too warm. But if too much heat escaped, parts of the station could become too cold. So the station has to release heat deliberately. Radiators send excess heat out into space as infrared radiation. Cooling systems move heat from inside the station to places where it can be radiated away. Insulation slows unwanted heat loss. Heaters protect equipment during cold periods. Nothing is random. Nothing is left to the vacuum, because space does not regulate for you. This is one of the great differences between Earth and orbit. On Earth, if a room becomes too warm, air can circulate, walls absorb heat, windows can open, and the surrounding environment helps carry energy away. In orbit, outside the spacecraft, there is no air to carry heat. A spacecraft cannot simply open a window to let warmth drift out into a breeze. There is no breeze. Heat must be moved through solid materials, fluids inside pipes, or released as radiation. That makes cooling strangely difficult. People often assume that because space is cold, Cooling should be easy, but the vacuum makes it harder in some ways. You cannot rely on air. You cannot rely on convection. You need surfaces designed to radiate heat away efficiently. You need to point them in the right directions. You need to protect them from direct sunlight when needed. You need to make sure the heat goes where you want it to go. In space, heat is not removed casually. It is engineered. This is why spacecraft often have strange-looking surfaces. White panels reflect sunlight. Shiny coatings reduce absorption. Dark radiators release heat. Gold-colored insulation reflects radiation and slows heat transfer. Multi-layer insulation wraps parts of spacecraft like delicate metallic blankets. These materials are not only for appearance, they are part of the spacecraft's survival. A simple color change can matter. A dark surface absorbs more sunlight. A light surface reflects more. A shiny surface behaves differently from a rough one. A surface facing the sun behaves differently from one facing deep space. A spacecraft is designed almost like a living organism, with skin that responds to radiation. But unlike a living organism, it cannot heal itself easily. If the thermal balance fails, the mission can suffer. A frozen component may stop working. A battery may lose performance. A camera may become distorted. Fuel may become too cold. Electronics may overheat. Sensitive instruments may produce bad data. Even small temperature problems can become serious when a spacecraft is millions of kilometers from repair. This is why space missions are planned with such care. Every orbit, every shadow, every rotation, every surface, every instrument, every heater, every radiator matters. And for astronauts, the challenge becomes even more personal. A spacesuit is often described as clothing, but that is far too simple. A spacesuit is a miniature spacecraft shaped around the human body. It must provide pressure, oxygen, carbon dioxide removal, temperature control, communication, mobility, and protection. It must allow a human being to exist where the human body cannot exist naturally. Thermally, the suit has a difficult job. In sunlight, the outside of the suit can receive strong solar radiation. In shadow, it can lose heat into space. Inside, the astronaut's body is constantly producing warmth. Movement, breathing, and work create heat. Without cooling, an astronaut can become too hot inside the suit, even while outside the suit is surrounded by cold vacuum. That is the paradox again. Space is cold, but an astronaut can overheat. The problem is not only keeping heat in, it is also getting extra heat out. On Earth, sweat evaporates and air carries heat away from the body. Wind helps. Clothing can trap warmth or release it. But inside a sealed suit, the body's heat has to be managed through technology. Cooling garments, circulating fluids, ventilation, insulation, and suit systems all work together to keep the astronaut within a safe range. The suit does not simply fight cold, it fights imbalance. That is what space creates, imbalance. Direct sunlight and shadow, internal heat and external cold, radiation coming in and radiation going out. A human being survives only because the suit creates a stable middle ground. Without that middle ground, space offers no comfort. This is also why astronauts do not experience space as a normal temperature. You cannot step into the vacuum and say it feels like a cold day in winter. There is no air to feel. There is no wind on your face. There is no atmosphere pressing against your skin. The danger is not a cold breeze. The danger is exposure to vacuum, radiation, lack of oxygen, pressure loss, and uncontrolled heat exchange. Space is not winter. Space is absence. An absence of air, an absence of pressure, an absence of the thermal systems that make Earth livable. And in that absence, the sun becomes both friend and danger. Without the sun, Earth would freeze. Without sunlight, spacecraft would lose a major source of energy. Solar panels depend on it. Many missions use the sun as power. But sunlight in space is unfiltered. There is no thick atmosphere to soften ultraviolet radiation. No clouds, no blue sky, no weather. A surface in direct sun receives raw energy. So spacecraft must decide how much sunlight to accept. Solar panels need sunlight, but instruments may need shade. A telescope may need darkness, but batteries may need warmth. One part of a spacecraft may want to face the sun, while another part must hide from it. This creates some of the most elegant engineering in modern astronomy. The James Webb Space Telescope is a powerful example. It was designed to observe faint infrared light from the universe, which means it must remain extremely cold. If the telescope itself were warm, its own infrared glow would interfere with the signals it is trying to detect. So it uses a large sun shield to block light and heat from the sun, Earth, and Moon. One side faces the sun. The other side stays cold. In space, because there is no air to carry heat around the shield, the difference between the warm side and the cold side can be extreme. A thin barrier can separate sunlight from deep cold in a way that would be impossible on Earth. The telescope survives by creating an artificial shadow, a controlled night in which its instruments can work. This shows the strange usefulness of cold space. The same cold that makes survival difficult can make observation possible. A cold telescope can see faint heat from distant galaxies. A shadowed instrument can detect weak signals. A spacecraft can release waste heat into the darkness. The universe's coldness is not only a threat, it is also part of how we study the universe. But it must be handled carefully. Every mission uses the cold and fears it at the same time. Farther from the sun, the challenge changes. In the outer solar system, sunlight is weak. Spacecraft traveling to Jupiter, Saturn, Uranus, Neptune, or beyond cannot depend on the same solar energy that works near Earth. Solar panels become less effective as sunlight fades. Temperatures drop. Instruments and fuel systems must be protected. Some missions use radioactive power sources that generate heat and electricity over long periods. In deep space, heat becomes precious. A spacecraft far from the sun may need to conserve warmth. It may use internal heat from electronics. It may insulate itself carefully. It may rely on small heaters to keep instruments alive. Far from Earth, far from the sun's strong energy, a mission becomes a fight against the slow loss of heat into the dark. The farther we travel, the more the sun becomes a distant lamp, still powerful at its source, but diluted by distance. At Earth, sunlight is abundant. At Jupiter, much weaker. At Saturn, weaker still. At Neptune, the sun is so far away that it looks more like a brilliant star than the overwhelming disk we know from Earth. The sun has not changed. the distance has. This is why the outer solar system feels like another reality. There, the planets move through faint sunlight. Moons are frozen. Rings shine softly. Shadows are long and cold. A spacecraft traveling there is moving through a realm where solar warmth is no longer generous. And beyond that lies interstellar space. The space between stars is even more extreme, not because there is no energy at all, but because energy is spread so thin. A lonely object drifting between stars receives faint light from distant suns and the weak ancient glow of the cosmic microwave background. Unless it has internal heat, it will slowly cool. It becomes part of the cold background of the galaxy. That is the fate of many objects. Rogue planets, comets, dust grains, dead spacecraft, small bodies moving far from stars. They drift in darkness, losing heat, receiving little in return. Some may still have internal warmth for a time. A large rogue planet could hold heat inside for billions of years. A moon or planet with radioactive decay or tidal forces may remain active beneath a frozen surface. But the general rule remains: without a strong energy source, the universe is cold. And yet, cold does not always mean still. This is another important idea. A world can be frozen outside and alive with energy inside. Europa, far from the sun, may hide a liquid ocean beneath its ice. Enceladus, small and distant, releases plumes from beneath its frozen shell. Some objects are warmed not by sunlight, but by gravity. Tidal forces flex their interiors, creating heat deep below the surface. So even in cold space, warmth can hide. Not on the surface, not in the sunlight, but below. This is one of the reasons space remains mysterious. Our eyes see frozen exteriors, but physics may create hidden oceans, buried chemistry, and slow internal motion. The coldness of space does not end all possibility. It only changes where warmth can survive. Earth's warmth is on the surface. Europa's possible warmth is hidden below ice. Venus has too much trapped heat. Mars has too little. The moon has extremes. Every world is a different answer to the same question. What happens to energy here? That is the question behind temperature. Not simply hot or cold, but energy received, energy stored, energy moved, and energy lost. The sun is only the beginning of the story. The object completes it. This is why Earth feels so extraordinary in part 4 of this journey. Our planet does not merely receive sunlight. It turns sunlight into a livable climate. It distributes energy through air and oceans. It stores heat in water. It releases heat into space. It balances incoming and outgoing radiation in a way that has allowed life to persist for immense spans of time. Earth is not just warmer than space. Earth is organized against space. It is a thermal sanctuary, a moving, breathing, cloud-wrapped system between a hot star and a cold universe. The atmosphere is part of that sanctuary. It filters sunlight, traps some heat, and lets some escape. The oceans are part of it. They absorb energy and move it around the globe. Ice is part of it, reflecting sunlight. Clouds are part of it, both cooling and warming depending on their height, thickness, and position. Life itself has become part of the system, shaping the atmosphere over billions of years. Nothing like that exists in the empty vacuum nearby. Just above the atmosphere, the environment changes completely. A few hundred kilometers above our heads, The International Space Station circles Earth in a place where humans cannot survive without walls and machines. It is close enough to see continents, oceans, lightning, clouds, and sunrise after sunrise. But outside the station, there is no breathable air, no normal pressure, and no natural comfort. The difference between Earth and space is not far away. It begins just above us. That is humbling. We often imagine space as distant, but the hostile vacuum begins surprisingly close. The blue atmosphere that protects us is thin compared with the size of Earth. From orbit, it appears like a delicate glowing edge. Almost all life exists below that thin line. Above it, the rules change. Below it, heat is weather. Above it, heat is radiation. Below it, sunlight becomes climate. Above it, sunlight becomes exposure. Below it, shadow is shade. Above it, shadow can be deep cold. This thin boundary is one of the most important things in our lives, and most of the time we forget it is there. We forget because it works. We breathe without thinking. We feel warmth without calculating radiation. We walk in shade without fearing deep cold. We live inside Earth's systems as if they are ordinary. But they are not ordinary in the larger solar system. They are rare and delicate. Space reminds us of that by removing them. When we send astronauts beyond the atmosphere, we wrap them in machines that imitate the missing world. When we send spacecraft, we cover them in materials that manage energy. When we build telescopes, we shield them from sunlight. When we explore the outer planets, we carry power and heat with us. Every mission is a small act of resistance against the natural cold emptiness around us. This does not make space evil. It is not cruel in a human sense. It is simply indifferent. The vacuum does not try to freeze or burn. The sun does not try to help or harm. The darkness does not notice us. The laws of physics do what they do. Energy moves. Matter absorbs. Surfaces radiate. Shadows cool. Light warms. Distance weakens radiation. And life must build a shelter inside those laws. Earth is our first shelter. Technology is our second. This may be the most important lesson of all. The reason humans can even ask why space is cold is because we live in a place that protects us from the answer. We are warm enough to wonder because Earth catches sunlight and holds it carefully. We are alive because our planet has not lost too much heat or trapped too much. We are conscious because a thin atmosphere and a stable star created a long window of possibility. Outside that window is the raw universe. Beautiful, immense, silent, cold, but not cold because the sun is weak. Cold because most of the universe has almost nothing in it to catch the sun's warmth. Cold because distance spreads energy thin. Cold because objects lose heat into a background only a few degrees above absolute zero. Cold because without matter, there is no comfort. And yet, in that same cold universe, stars burn. Planets warm. Moons hide oceans. Spacecraft survive. Telescopes see ancient light. Astronauts float inside tiny artificial worlds. And Earth continues to turn beneath its blue atmosphere, balanced between the furnace of the sun and the darkness that waits beyond. That balance is fragile, but it is also beautiful, because every sunrise is part of it. Every warm breeze, every cloud, every ocean current, every tree growing from sunlight, every human hand warmed by daylight. All of it exists because Earth knows how to live between fire and cold. The sun gives, space takes away. Earth holds just enough. And that is why our planet, small as it is, feels like a miracle inside the frozen architecture of the solar system. The answer to this question becomes clearer the farther we travel from Earth. Why is space so cold when the sun is so hot? At first, it sounds like a contradiction. The sun is a star, a vast sphere of plasma, releasing unimaginable energy every second. It is powerful enough to warm Earth from 93 million miles away. It is bright enough to light the moon, heat the planets, drive weather, grow forests, and shape almost every living system on our world. And yet, the darkness around the sun remains cold. Not because the sun is weak, not because its heat disappears, but because space is not a warm room. It is almost empty. That is the heart of everything. The sun sends energy outward as radiation. That radiation can cross the vacuum easily. It does not need air. It does not need water. It does not need a surface. It can travel for millions of miles, billions of miles, even light years, moving silently through darkness. But radiation only becomes warmth when something catches it. A planet catches it. A moon catches it. A spacecraft catches it. A grain of dust catches it. Your skin catches it on Earth after it passes through the atmosphere. But empty space itself has almost nothing to catch. This is why sunlight can fill the solar system and still leave the solar system mostly cold. The light is there, but warmth belongs to matter. Warmth belongs to surfaces, particles, atmospheres, oceans, rocks, clouds, and bodies that absorb energy and hold it for a time. Space does not hold it well. Space lets it pass. This changes the way we should imagine the solar system. It is not a giant heated room with the sun at the center. It is more like a dark, nearly empty hall with a powerful lamp shining inside it. Anything directly in the lamp's beam can warm. Anything in shadow can cool. But the hall itself is not filled with warm air, because there is no air. That is why the moon can be hot in sunlight and freezing in darkness. That is why Mercury, so close to the sun, can still have extreme cold in places hidden from sunlight. That is why a spacecraft near Earth can overheat on one side and freeze on another. That is why astronauts need suits that control both heat and cold. That is why Earth is not simply lucky to be near the sun, but lucky to have the right systems to use the sun. Earth is not warm only because sunlight arrives. Earth is warm because it catches sunlight, moves it, stores it, softens it, and releases it slowly. Our atmosphere is part of this miracle. It surrounds the planet like a living shield. It scatters sunlight into blue sky. It blocks harmful radiation. It carries heat through winds. It traps some infrared energy. It allows clouds to form. It keeps nights from becoming like the airless darkness of the moon. The oceans are part of it too. They absorb enormous amounts of heat. They move warmth around the planet through currents. They release energy slowly. They make coastal climates gentler. They connect the sun's energy to weather, storms, rain, and life. The land is part of it. The ice is part of it. The clouds are part of it. Even life is part of it. Earth is a system that turns sunlight into habitability. That is rare, because most places in space do not do this. Most places either cannot hold warmth, or hold too much, or receive too little, or have no atmosphere, no liquid water, no protection, no pressure, no balance. The solar system is full of worlds that show us different answers to the same question. Mercury receives intense sunlight, but without a real atmosphere, it cannot spread that warmth gently across the whole planet. Its surface becomes a place of extremes. Venus receives sunlight and traps heat so strongly that its surface becomes a furnace. Mars receives less sunlight and has too little atmosphere to hold warmth well, so it remains cold and dry on the surface. The Moon receives almost the same sunlight as Earth, but without air or oceans, it swings between burning light and deep shadow. The outer planets receive only a faint fraction of Earth's sunlight, so they exist in a realm where the sun is distant and weak. Each world teaches us that sunlight alone is not enough. The real question is always, what happens to the energy after it arrives? Does the world absorb it, reflect it, trap it, move it, lose it, store it, transform it? Earth's answer is life. That is what makes our planet so extraordinary. Around us is a universe that is mostly too cold, too empty, too exposed, too violent, or too unstable for life as we know it. And yet here, on one small world, sunlight becomes warmth. Warmth becomes weather. Weather becomes water cycles. Water cycles become rivers, forests, oceans, and living cells. The coldness of space makes Earth feel even more precious, because it reminds us that warmth is not the default state of reality. The default state of most of the universe is not comfort, it is distance, vacuum, radiation, darkness, sparse particles, thin gas, frozen worlds, airless surfaces, objects losing heat into a background only a few degrees above absolute zero. Earth is a small exception, a blue exception, a warm exception, a place where the sun's energy is not too weak, not too strong, not trapped beyond control, and not lost too quickly. We live in the narrow balance between fire and cold. The sun is the fire, space is the cold, Earth is the balance. And that balance never stops working. Every second, sunlight arrives at Earth. Some of it reflects back into space from clouds, ice, oceans, deserts, and the atmosphere. Some of it is absorbed by the ground and sea. The warmed planet then releases energy back outward as infrared radiation. Some of that escaping heat is absorbed and re-emitted by greenhouse gases. Some escapes into space. This constant exchange is what keeps Earth from becoming too hot or too cold. The planet is always receiving, always releasing, always adjusting. It is not frozen because the sun warms it. It is not burning because it can radiate heat away. The coldness of space is part of what allows Earth to cool. Without the dark universe around us, there would be nowhere for excess heat to go. A planet needs warmth, but it also needs a way to lose warmth. Life depends on both. That is a beautiful contradiction. The cold of space is dangerous, but it is also necessary. If Earth only absorbed sunlight and never released heat, it would not remain habitable. If Earth released too much heat and held too little, it would freeze. Life exists because the exchange is balanced enough, for long enough, under the right star, at the right distance, with the right atmosphere. This is why the question is not only scientific, it is emotional. Why is space so cold when the sun is so hot? Because heat is not just produced, it must be caught. Because light is not the same as warmth. Because vacuum does not behave like air. Because the universe is too empty to become a comfortable place. Because stars shine into darkness, and only the objects that receive them become warm. This changes how we see the sun. The sun is not a heater warming a room. It is a star sending energy into a void. Most of that energy travels outward and never touches Earth. It passes planets, crosses empty regions, spreads thinner and thinner, and eventually joins the faint radiation of the galaxy. Only a tiny fraction lands on our world. And from that tiny fraction, Earth builds almost everything familiar to us. Daylight, rain, wind, food, breath, forests, oceans, clouds, human life. The sun gives us energy, but Earth gives that energy meaning. Without Earth's atmosphere, sunlight would not feel like a warm afternoon. It would be raw radiation striking an exposed surface. Without oceans, there would be no great storage of heat. Without pressure, water would not behave the way life needs. Without the right chemistry, sunlight could not become biology. So the sun is necessary. But Earth is the translator. It translates starlight into life. Space cannot do that. Space is too thin, too empty, too wide. It lets the light pass through. This is why astronauts do not go into space wearing simple, warm clothing. A winter coat works on Earth because it traps warm air near your body. But in space, there is no outside air, no pressure, no breathable atmosphere, and no natural thermal stability. A spacesuit must do far more than keep someone warm. It must create pressure, provide oxygen, remove carbon dioxide, protect from radiation, manage cooling, reflect sunlight, and preserve the body inside a narrow range. A spacesuit is not a coat, it is a tiny Earth. And a spacecraft is the same. Every spacecraft is a small artificial world fighting against imbalance. Its sunlit side may heat, its shadowed side may cool, its electronics create warmth, its instruments need protection, its radiators must release excess heat, its insulation must stop heat from leaving too quickly. The spacecraft survives only by carefully controlling how energy enters, moves, and leaves. This shows us something profound. Space is not naturally livable. Life in space requires design. On Earth, nature already designed the system for us over billions of years. We were born inside a planet-sized thermal machine. We do not notice it because it has always been around us. The air touches us, the sky protects us, the oceans store heat, the ground supports us, the sun rises and sets through a thick atmosphere that makes daylight gentle enough to live under. We call this normal, but it is not normal for the universe. It is normal only for us. Beyond the atmosphere, the truth is waiting. A vacuum where heat cannot move by wind. A darkness where shadow can become deep cold. A sunlight unsoftened by blue sky. A universe where every object must solve the problem of temperature alone. And still, the coldness of space is not empty of beauty. It is the reason stars stand out so sharply. It is the reason infrared telescopes can look deep into cosmic history when shielded from the sun. It is the reason comets can preserve ancient ice. It is the reason some shadowed craters may hold frozen records of the solar system's past. It is the reason planets can release heat into the universe and maintain balance. Cold is not only an enemy. Cold is part of the structure, part of the exchange, part of the silence that makes warmth meaningful. A candle matters because the room is dark. Earth feels precious because space is cold. The sun feels miraculous because the universe around it is mostly empty. When we imagine the solar system from far away, we should picture not a warm, glowing bubble, but a cold ocean interrupted by islands of energy. The sun burns at the center, planets move around it, moons cast shadows, asteroids tumble, comets sleep in darkness, spacecraft drift through vacuum, and between everything is distance, enormous distance, the kind of distance that thins sunlight, delays communication, and makes warmth rare. Near Earth, the sun feels dominant. It fills our days. It defines our seasons. It sets the rhythm of life. But in the outer solar system, the sun becomes smaller. At Jupiter, the sunlight is weaker. At Saturn, weaker still. At Uranus and Neptune, it is pale and distant. Far beyond, it becomes only one bright star among many. The sun is still hot, but distance makes its warmth harder to catch. That is the second great truth. Space is cold because it is empty, and space becomes colder with distance because sunlight spreads out. The farther energy travels from the sun, the more widely it is distributed. The same star that can warm Earth cannot warm Pluto in the same way. The same light that powers forests here becomes faint at the edge of the solar system. The same radiation that can overheat a spacecraft near Earth becomes too weak for easy solar power far away. The solar system is not one thermal environment. It is a gradient, a long fading of sunlight into darkness. And Earth sits in one of the most fortunate regions of that gradient, close enough to receive strong sunlight, far enough not to be overwhelmed by it, massive enough to hold an atmosphere, active enough to have oceans and weather, stable enough for life to endure. This is why the coldness of space should not make us think the sun is less powerful. It should make us understand how rare it is for a planet to use a star's power well. Venus receives sunlight and becomes trapped in heat. Mars receives sunlight and loses too much warmth. The moon receives sunlight but cannot spread it. Earth receives sunlight and turns it into a living world. That is the difference. Not the sun, the world. Every world is a conversation with its star. Earth's conversation has been gentle enough for life. For billions of years, this planet has kept a delicate exchange with the sun and space. It has accepted enough energy to avoid freezing and released enough energy to avoid burning. It has changed, yes. It has passed through ice ages, warm periods, volcanic ages, impacts, extinctions, and climate shifts. But through all of that, it remained within the broad possibility of life. That is astonishing, because the universe outside does not promise such balance. It offers extremes, the bright side of an airless moon, the dark floor of a shadowed crater, the frozen surface of a distant dwarf planet, the intense heat of a world too close to its star, the crushing atmosphere of a runaway greenhouse planet, the empty cold between stars. Earth is not like most places, and perhaps this is where the answer finally becomes quiet. Space is cold when the sun is hot. Because warmth is not everywhere. Warmth is local. It appears where energy is caught, shaped, and held. The sun pours energy into the solar system, but only certain places can turn that energy into something stable. Earth is one of those places. For now, a blue planet wrapped in air, balanced between radiation and darkness, carrying oceans beneath clouds, receiving sunlight by day and releasing heat by night, constantly speaking to the universe in waves of energy. The cold space above us is not separate from this balance. It is part of it. Every night, Earth radiates heat into that darkness. Every day, sunlight replaces what is lost. The planet breathes thermally, in and out, across the boundary between atmosphere and space. Receive, release, warm, cool, balanced life exists inside that rhythm. And maybe that is the most beautiful way to answer the question. The sun is hot enough to give life energy. Space is cold enough to take excess heat away. Earth is balanced enough to live between them. We are not simply living near a star. We are living in a narrow agreement between fire and emptiness. When you feel sunlight on your skin, you are feeling energy born in the heart of a star. That energy crossed space, passed through the atmosphere, touched Earth, and became warmth. Around that moment is a universe mostly too cold and too empty to hold you. But here, for now it does. Here there is air. Here there is water. Here there is ground. Here there are clouds. Here warmth can stay long enough to become life. So the next time the sun rises, it may feel different. Not just bright, not just warm, but extraordinary. A star sending energy across a cold void. A planet catching that energy. An atmosphere softening it. An ocean storing it. A living world turning it into breath. And beyond the blue edge of that world, space remains silent and cold. Not because the sun has failed, but because emptiness cannot hold warmth the way Earth can. The sun burns, the universe waits, and between them, our small planet glows. Good night.